Okay, good morning, everyone. Let's dive right in. Orientation. Undergrads, you're working on assignment 4. Grads, you're working on 7 and 8. Everything okay with the assignments? Thumbs up. Excellent. Okay, so we will finish up today lecture 7, a very brief history of the field. That's going to cover the first 2 experiments in the mid-90s, and then we will move into lecture 8 today, which is going to cover a particular flavor of neural networks, which we'll talk about, that were used in the minimal cognition experiments, and these CTRNNs are still used today in robotics for various purposes. As you'll see shortly, CTRNNs have certain advantages over traditional neural networks when they're trying to transform sensation into action. Okay, back to lecture 7, the first years of evolutionary robotics. We were starting to describe arguably the very first evolutionary robotics experiment using this hockey puck-sized Kepra robot. We talked a little bit about how it's going to run around on a tabletop. The evolutionary algorithm and the neural network controlling the robot are running on a desktop to which the robot is tethered. We talked a little bit about the neural network sitting inside this Kepra robot. The investigators set some of the parameters, like which synapses are excitatory and which are inhibitory, but they left the other parts of the design task or the optimization task to the evolutionary algorithm, which in this case is to set the magnitudes of the synaptic weights. And they've dreamed up something for their robot to do on top of this desk, which is to circle around and around the maze as fast as possible without hitting the walls. So the evolutionary algorithm is going to drop sets of synaptic weights into this Kepra robot, one set of weights after another, and the desktop is going to need a fitness function, some way to evaluate how well or how poorly that set of synaptic weights causes the robot to circle around the maze and not hit the walls. Okay. So I ended last time by giving you some optional homework to do, which is to dream up a fitness function. How do we actually give the computer an equation that it can compute to determine how well or how poorly the robot is doing or what we want it to do? We're going to compute that fitness function from values of the sensors, specifically the values of the 8 proximity sensors. A firing of 0 means there's no obstacle or obstacles are really, really far away. That sensor can range between values of 0 and 1, where 1 is the proximity sensor is right up against some obstacle. We're going to assume I1 through I8 are these 8 proximity sensors, the 6 on the front, the 2 on the back, and we'll assume that these are average values. For the 10 or 15 seconds that the robot is running around in the maze with a given set of synaptic weights, what are the average values of those 8 sensors? Okay, we can also use a 9th and 10th variable, which is the average rotational speed of the left and right wheel, VL and VR. We'll assume for our purposes that VL and VR can range between minus 5 and minus 0.5 and plus 0.5. Rotate backwards, 0 is the motor isn't spinning, plus 5 is it's spinning forward. Again, we'll assume VL and VR are the average rotational velocities or the average speeds of the 2 wheels over those 10 or 15 seconds. Okay, ideas. How do we go about constructing this fitness function?
So when I did mine, I didn't realize that proximity sensors were averages.
Oh, okay.
But so I have in parentheses absolute value of the motor, the left motor, plus the absolute value of the right motor, and then times 1 minus I1, and then just repeat that for all the I's, for all the sensors.
Something like this?
Yeah.
Okay. Tell us about the overall terms. Why are you multiplying these terms together?
So if it touches a wall, that means it's unfit.
Okay, so if it touches a wall...
If any of those are 1, that means it hit a wall, which means it failed. And then the motor one, it's trying to, the more the motor spins, I'm assuming it's the faster it goes.
Okay.
So it's maximizing speed and minimizing wall contact.
Okay. This looks pretty good. Let's give this a try. So in your head, I want you to imagine this robot moving around in the maze and these values arriving at these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 variables. Will larger values of phi indicate robots that are doing a better job of circling through the maze as fast as possible and not hitting the walls? And will lower values of phi indicate the robot's doing a worse job at that?
I think it could have a pretty high value and just be going in like circles if both wheels are like max speed in the opposite direction.
Okay, so pretty good. Could be that the average speed of this wheel is spinning forward really quickly, depending on the set of synaptic weights. And it could be that VR is spinning backwards really quickly, which would end up with the robot spinning in place. If we take the absolute values and sum them, we get a high value.
We could just remove the absolute values from both of them and do the absolute value of their sum instead. So it would be VL plus VR in the absolute value of that.
The absolute value of the sum. What we're doing right now is one of the oldest traditions in evolutionary robotics and robotics in general, which is we came up with a pretty good way of trying to tell the computer how to tell the robots whether they're doing a good job or bad job. But it wasn't perfect. There were instances of perverse instantiation, which we have now caught before we've even run this experiment. And we're now trying to alter how we tell the computer to reward or punish the robots. This is known as, in evolutionary robotics, it's called fitness function engineering. We're sort of, it's like prompt engineering. We're trying to figure out how to tell the computer to do something that we want. And it's actually not that easy, even for a relatively simple robot in a simple environment. Okay, so we have a proposed improvement. How does this do? We closed one perverse instantiation loophole, which was to spin around on the spot.
I know we don't want it to hit the walls, but if this goes around very quickly and grazes a wall at the very end, the fitness will be 0 because it will have touched it with the multiplication.
Okay,
But, yeah.
and as was pointed out by the original proposer here, the assumption was these weren't averages. Assuming they are averages, if one of the proximity sensors grazes the wall right at the end, it's not going to have a big impact on the average, so maybe wouldn't be too much of a problem. How does this look? So if the robot doesn't go anywhere, VL and VR are 0, this term becomes 0, and those sets of synaptic weights will be evolved out of the population very quickly, so that's good. If the left wheel is spinning quickly and the right wheel is spinning quickly backwards, this term will also be 0, so that's good. We've closed the loophole of spinning in place.
I mean, if you're subtracting the distance from the wall from 1, if you're really close to the wall, it's going to be like, say you're like 0.1, however much distance from the wall, it's going to now be 0.9. Keep multiplying that by the sensors, it could end up, because you're still going to have a higher number when you're closer to the wall, because it's a subtraction, it's going to reward it for being closer to the wall when it's going around. You might want it to be more in the center.
Okay, possibly. So it could be that a lot of the sensors get kind of close to an obstacle, 0.1. So that's going to definitely decrease this value, which is probably good. It's putting some pressure on the evolving sets of synaptic weights to stay away from the wall. This is actually pretty good. Here's what the investigators came up with. I actually like this better. I think this is a little more elegant. You'll notice that they have 3 terms. 1, 2, 3. We'll take each one at a time. They defined I, and they dropped the subscript. So this is the maximum firing proximity sensor across all the proximity sensors. I restricted you to I1 through I8, the average value of the 8 proximity sensors. So they're cheating here a little bit. They're looking for, across all the sensors, at every time step in that 10 to 15 seconds, what was the worst offender? Maybe I3 got particularly high at some point. That's the value that gets stored in I. Before I define these 3 terms, even just from the notation, the choice of variable letters, any guesses about what these terms do? This one I think we can already figure out, very much like the original proposal here, 1 minus I. So this term here is punishing any sensor, at any proximity sensor at any point in time for being overly high. So generally speaking, there is evolutionary pressure, meaning that as sets of synaptic weights are evolving over time, it's being punished for the worst offender. What about these other terms?
Seems like it's punishing like change in speed, sort of.
It's punishing change in speed. So V, as you can probably guess, is for velocity. Delta is a commonly used notation for change. So they're computing change in velocity somehow, and you mentioned punishing because there's a 1 minus, right? That's a good sign that it's trying to minimize this value. The value of the is trying to minimize this value. So punishing for approaching the walls, punishing for delta V.
Is delta V just the difference between the 2 wheels? So they're punishing for the case where it's just spinning in one direction?
Yes. So V itself is, like we heard before, V rewards for non-zero values of VL or VR. Maximize the magnitude of VL or VR. Make them very negative or very positive. But as we saw before, this can lead to turning in place. So delta V here is basically the difference between VL and VR. They're normalizing a little bit, which doesn't really matter for our purposes. I like this better because this combines their first and second term. We'll come back to the square root in a second. Okay, square root of delta V. So we're taking delta V, and then we're taking the square root of it. So a little detail here in the fitness function. What taking the square root does is it places strong weight in small differences. So in the initial random population of sets of synaptic weights, if some of them produce a slightly less delta V than others, they're doing a little bit better job at equalizing the turning of the 2 wheels. You take the square root of 2 slightly different delta V values, and it magnifies that amount. Remember, the square root function looks something like this. So if this is delta V on our horizontal axis here, and this is the square root of delta V here, if we have 2 individuals in the population that have slightly different delta Vs, one of them has slightly more than the other, that amount is going to be magnified by the square root value. So they're kind of telling the evolutionary algorithm, really exert evolutionary pressure even on slight differences between delta V. It's kind of a detail, but just you can see the investigators here doing this fitness function engineering, trying to get these terms just right. Any questions about this fitness function before we move on? Yes?
Just in general, is like V and delta V like the average of the differences, or is it the max as well, like I?
This is VL and VR. These are the averages. Yeah, averages, and then it's only the I that's the worst offender. As we just saw, there's no one right fitness function. There are many fitness functions that will basically get you what you want, and there are many, many more fitness functions that will give you perverse instantiation. They'll maximize phi with some sort of behavior, like spinning in place, but that's not, in retrospect, what you wanted. Part of the fun and the agony of robotics, which you'll find when you get to your final project, is it's notoriously difficult to tell the evolutionary algorithm what behavior you want without specifying the behavior itself, right? These are the investigators struggling to tell the evolutionary algorithm, evolve a robot that circles around the maze and doesn't hit the walls. Do it like this, but not like this, and 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 not like this. In the end, you almost wish you could just sit down and tell the robot what to do. Notoriously difficult to make this process hands-off. No one's come up with a good way to make this very hands-off and end up with a reliable, autonomous, and safe machine. Okay, details of the fitness function, not so important for today. The message here is how difficult it is to get this right. Okay, they did get it right. Remember, this is the mid-90s, so commercially available physics engines weren't around yet. So they took each set of synaptic weights and ran it on the physical robot. There's no simulation here. They had a population of, I don't remember, I think it was 100 or 150 sets of synaptic weights. To evaluate each one of those, took 10 to 15 seconds, reset the robot, download the next set of synaptic weights, let it run around for 10 to 15 seconds, reset the robot, round and around and around. So to evaluate one generation of synaptic weights took 40 minutes. At the end of that generation, they delete the sets of synaptic weights that had low phi. So I'm just going to draw this as dashes, feeling a little bit lazy this morning. I'm going to put uppercase T on the horizontal axis here. Here's one set of synaptic weights, another set of synaptic weights. This took 40 minutes to run. Then they delete the robots with lower phi and made randomly modified copies of the sets of synaptic weights that had a higher value of phi. What do I mean by lower or higher? Lower than the average in the population at this point. You can imagine with 100 or 150 sets of randomly generated synaptic weights, the robot did a terrible job of this. It would sit still, it would jitter and then sit still, it would drive straight and smash into the wall, it would drive straight, drive back, drive straight, drive back, a gazillion ways to not do this. Most of those sets of synaptic weights generated very low values of phi, but some values were a little bit less crappy than other values of phi. So they repeated this process again. They evaluated all these new individuals for another 40 minutes and another 40 minutes. I don't know if I did my math here or not, but after running 100 generations of this on the Kepler robot, after 66 hours of experimentation time, or a little less than 3 days, they got this, and we'll talk about this in a moment. I want you to put yourself in the shoes of the investigators. Luckily, they didn't do this all at once. It's still a pretty manual process. They're they're sending motor commands to the robot. The robot moves. We get the X, Y, and orientation of the robot back from the little laser that's pointing down onto the desktop. Repeat, repeat. Then they got to move the robot back, untangle some of the wires, put the robot back at this point in the maze, facing in the direction it was facing before, do it all again, do it all again. It's a manual, repetitive, mind-numbingly boring thing to do for 66 hours. Yeah? Okay, you can understand why when physics engines arrived, people got pretty excited. We didn't have to do this all directly here in the real world. Okay, so again, I apologize for the quality of this plot. It's a little old now. On the horizontal axis here, we have time, evolutionary time. Time in generations, 100 generations. And on the vertical axis here, we have phi, and you can see that phi is generally climbing over evolutionary time. It's nearly impossible to see from this plot, but read off from this plot. This curve here is the average value of phi inside the population at that moment in evolutionary time. And this higher plot here is the maximum value of phi. Who had the highest value of phi in the population at that time? Yeah. You'll notice these little vertical lines here. These are error bars. So they actually did this multiple times. They did this once, and it took them a little less than 3 days. Then they went back to the beginning, generated a new set of a new random population, did it again for another 3 days, another 3 days, another 3 days, which gave them a general sense of, on average, when you start with a bunch of random sets of synaptic weights, how does phi climb over 100 generations or 3 days of wall clock time? Okay, a lot of human effort in this plot. Okay, here's the best of the best. Among all these runs of all the sets of synaptic weights, they took the set of synaptic weights that got the highest value of phi, dropped it back into the robot, and very carefully took a whole bunch of photographs and then threw the photographs away and created this plot. Every individual line segment here, the centroid of that line segment represents where the robot was at that moment in time, and the orientation of that line segment indicates the orientation of the robot at that point in time. How's the robot doing? This is the pre-YouTube era, so unfortunately we don't have a video of this robot. You got to picture this robot moving around in the maze given this figure. How's the robot doing? Okay, I got thumbs up. It's not staying in place. Okay, I see a side thumb. Good. It's definitely not optimal. Why is it not optimal?
It's getting pretty close to the wall, especially on the turn where it's got a lot of room to move where it could stay away from that and not risk hitting a wall.
That's it. So the spacing between contiguous line segments also tells you a little bit about velocity. It's a little hard to see. It kind of speeds up a little bit, slows down, a little bit wobbly. It's actually going kind of fast here, slows down, slowly turns around, and then jets off up the next part of the maze. So sort of speeding up, slowing down, almost bumping into the wall. This is a reminder that biological evolution and artificial evolution, she's a satisfier, not an optimizer. You may not know this, but you are not optimal. There's a lot of things about your physiology and your neurophysiology that's not perfect. Same for every other organism on the planet, and same for every evolved robot we're going to see in this course. The evolutionary algorithm is good at improving phi or improving fitness over time, but we have no idea what the optimal value of phi would be. In order to know what the optimal value of phi would be, we'd have to take all of these floating point values, this vector of floating point values, and consider every single vector of that length of floating point values, which is effectively infinite. Hard to know, basically impossible to know what the optimal is.
With quantum computing, if we could get that working consistently, would we be able to get, for obviously not for larger things, that'd probably still be pretty hard, but for something like that, find the optimal values?
If we have quantum computers, could we actually do this? That's the dream. We'll see. We'll see.
Do the weights reflect that specific maze, or would they be able to generalize?
Great question. What do you think? So this set of synaptic weights produces this behavior in this maze.
Could maybe generalize poorly.
Maybe.
Probably do
Yep.
some of it though, but not as well as it can do the maze it was trained on.
Maybe. So we drop this into an autonomous vehicle and we put you in the vehicle in the streets of downtown Manhattan, in which, in essence, you're in a maze. I wouldn't want to be in that vehicle, right? Again, this is why robotics and AI are still a super interesting field to work in. No one has an answer. It's impossible to know whether this will generalize or how well it will generalize. Maybe it will do well to a set of mazes that are kind of like this, but terrible in mazes that are less like this. Hard to say unless you actually try it. Yeah. Part of the non-optimality of this solution is it's also not completely general. Very, very good question. No one has a good answer to that yet. Okay, back to this particular controller, this set of synaptic weights. Is this robot driving forward or backwards? Can't tell from the figure, right? It seems obvious to us that evolution would produce a robot that drives forward, obviously.
Is it driving backwards because it's much less likely, there's fewer proximity sensors in the back, so if it bumps in the front, then it's less likely to hit something, or like actually have a higher weight?
Maybe. Do you move around like this? You got most of your proximity sensors facing this way, and that tends to be the direction we move in. So obviously that's what the robot would evolve to do as well. Thinking about thinking is misleading. I don't know, actually. I do know that in some runs, some of the evolutionary runs, they got maze racers that did it forward. And sometimes when they reran it from different sets of synaptic weights, they got robots that raced around the maze more or less just as well backwards. So at least for this simple robot, didn't matter too much. It seemed to be able to get along just fine by driving quote unquote backwards. For the robot's perspective, maybe there isn't really a front or back. Another reminder that, again, one of the fun things about robotics is often we get pretty good solutions, maybe near optimal solutions that are very different from what a human engineer would have sat down and programmed this robot to do. Yeah, sometimes forward, sometimes back. That's why they spent all this time on this fancy fitness function that didn't explicitly say go forward. It allows for going forward and going backwards. Yeah, okay. Question?
So, just a little back to when we were talking about its ability to generalize.
Yeah.
Could you make something better generalizing by changing the environment it's trained in each time?
Yes, so great question. So if we do want something that doesn't just work in this maze but generalizes to unseen mazes, what can we do? What you mentioned is the first and most obvious thing, which is don't just evaluate each set of synaptic weights in one maze, put it in 100 different mazes, calculate phi 100 times, and set the actual value of phi to the average of all those 100 phis, or maybe set it to the worst of all those 100 phis and keep going. The obvious thing to do, but as all obvious things, it's got an obvious drawback, which is
Efficiency, it's going to take a lot.
it's expensive, right? In machine learning, we talk about sample inefficiency. How many samples, or in our case, how many runs of the robot do we need to do to get it to generalize? Is there something more subtle we could do rather than just train it on a whole bunch of mazes to get it to generalize better? There are many proposed solutions that are more subtle that deal with this a little bit better, but in my opinion, none of them are very satisfying. Hopefully, there's still some better answers out there.
Could you, instead of just train like each individual model like 100 times, just have those 100 mazes, and each time you're doing a cycle of evaluating, randomly select a maze for all of them to do, and then make the next model select a new maze? Or would that affect like its performance poorly by seeing something else each time?
Great question. So I'm going to bend your solution a little bit. So original solution was evaluate every set of synaptic weights in 100 mazes. Let's do something else. Let's take each set of synaptic weights and evaluate it in a randomly chosen subset of 10 of those 100 mazes. Keep going. And then again, everybody sees a random set of 10. Better also has problems. And I'm going to just put a pin in this conversation here. Very, very important. We'll come back to this again later. It also has a bit of some problems. Okay. Any other questions? Okay. Again, I'm so sorry it's hard to see here. You'll have to trust me. We've still got evolutionary time on the horizontal axis here. And they're now plotting the three terms, v, 1 minus I, and 1 minus the square root of delta v. They're plotting those three curves for the best individual in the population over evolutionary time. What's going on here? Remember, we're ultimately multiplying the values of these three terms together to get the vertical axis up here. I saw a hand up.
It looks like it's getting faster.
Okay, so if we grab onto V, which is the solid line, it's getting faster. So over the first day of wall clock time, the robot's moving faster and faster. The wheels are spinning faster in the evolved sets of synaptic weights. What else is happening? Lots of things are happening. Let's have a look at the dotted line here, which is 1 minus delta V. It starts kind of high. The dotted line is here, and then it drops a little bit, and it stays at this value of about 0.4. We want all three of these terms to be as high as possible. We're multiplying these three terms together. It's actually dropping over evolutionary time. What's happening here? What's happening as these sets of synaptic weights are evolving?
It's following a straighter path.
Following a straighter path? 1 minus square root of delta V is dropping.
It's learning how to turn because the wheel speeds have to be different to turn.
It's got to turn, right? Can't keep the wheels spinning at the same velocity because you'll crash into the wall. So what you're seeing as speed goes up and the dotted line is coming down a little bit, this is evolution, the evolutionary algorithm trying to balance competing selective pressures. Us and all of our ancestors before us, they also experienced competing evolutionary pressures. There's advantages to get better or bigger or faster at some trait, but there's always a trade-off. It means you get worse at some other trait. What are some evolutionary trade-offs that the human species has had to pay? Again, we're not perfect. We are a struck bargain between different kinds of traits which allow us to survive long enough and hopefully produce offspring.
In order to survive better on land and the air, you can't breathe underwater.
Okay, we had to give up something, yeah. Okay, we breathe here, not under there, yep.
I guess like neurological things like ADHD or.
Could be.
Just like the brain itself, like because we're so like advanced brain-wise, it takes a lot longer for our youth to grow up.
Absolutely.
So more chance for them to die.
Absolutely, right? So evolution put a lot of eggs in this basket up here, right? There's something about raw intelligence that's useful. The cost is immaturity for longer. Great one. Okay, last one. We're going to talk about bipedal locomotion in a few lectures from now. Bipedal locomotion is fantastic from an energetic point of view. Remember us talking about how your leg, the muscles in your leg go limp for half of your stride? Super useful. It's allowed us to be very, very successful, or allowed our ancestors to be very successful on the African savanna, but we paid and are still kind of paying a very heavy cost for bipedal locomotion. What is it?
I mean, if you fall, that's a lot farther fall.
Okay, yes,
Do a lot more damage.
true.
It's a lot harder to walk on two legs, so you use more of your brain.
Okay, yeah, so there's been some costs about coordinating that. Yes, that's true. Much higher cost we're paying though. Speed? Yeah, true, we gave up speed. These are all costs, but not the ultimate cost, the heaviest cost we gave up for the evolution of bipedal locomotion. Bipedal locomotion required evolutionary changes to a lot of our physiology. Many of them were in our hips. What's the cost we paid? Or at least half of the members of our population risk paying.
Childbirth is harder.
Childbirth is harder.
Our babies are so undeveloped, they come out early.
Much more difficult. Childbirth is much more difficult in our species for various reasons, but mostly because of bipedal locomotion. So like in nature, as an evolutionary roboticist, you're often devising fitness functions that are rewarding or punishing for features of different traits. And then when you run your evolutionary algorithm, it's got to strike balances between those traits. You cannot have a robot that moves, that minimizes delta V, that drives as straight as possible, and doesn't hit the walls. It's impossible. One of those two terms has to give. In this particular run, it looks like speed got more favor than turning. Okay, I'm going to skip this. This was just another attempt by the investigators to show how evolution makes trade-offs between these three desiderata, these three terms. Okay. One last thing I wanted to say about this is they took their robot, threw away evolution, and then the investigators manually set the magnitudes of the synaptic weights. They wanted to see how they could do with their raw intelligence compared to evolution. The width of the lines now represents the magnitude. So a line with a thick line with this sign at the end is strongly inhibitory. A thick line with this symbol at the end of it is strongly excitatory. Thin lines have values that are near 0. You should be able to see immediately that they've made a bilaterally symmetric robot. The investigators basically took the Bratenberg vehicle and tried to set these weights, and they got a vehicle that does this. Compared to the vehicle that you just saw, which with the evolved sets of synaptic weights, starting here, moves like this. The evolved solution is better than their solution. Why? What's wrong with the manually designed solution? What's happening?
Maybe the evolved solution started like this, but it's had the opportunity to repeat and tweak itself more over and over till it isn't doing that and can reach the goal more.
Isn't doing what? What's the problem?
Staying in place.
Why is it staying in place? Why is the manually devised set of synaptic weights staying in place?
It looks like it's just spinning.
Not quite spinning.
It's kind of getting just stuck in the corner because all the sensors are like can't go forward.
Absolutely. So imagine there's a corner here in front of me. I'm the manually designed robot. I go forward, and I'm heading into the corner, but not exactly into the corner. This is the real world. Nothing is exactly symmetric. There's a little bit more proximity values coming in on this side. So as a Bratenberg vehicle, I turn away from the obstacle over here, and now there's a little bit more proximity over here. So I turn back the other way. The other sets of synaptic weights are trying to drive my wheels forward, so I end up getting stuck in the maze and can't get out. Bilateral symmetry. We're bilaterally symmetric. It's obvious that's the best solution. Let's build that into a robot. Thinking about physiology in this case is, again, misleading. The evolved sets of synaptic weights are almost symmetric, but not quite. There's a little bit of asymmetry in there, and it turns out that it's probably, I was going to say intentional. Evolution is not intentional. There's a reason why there's a little bit of asymmetry in there. Again, not something that a human engineer would immediately put in there, but it turns out to be useful. Question? Okay, last mystery before we move on to another experiment. The very best evolved controller, or some of the best evolved controllers, they only ever drove the robot at a maximum speed of 48 millimeters per second. But the motors themselves could turn the wheels up to 80 millimeters per second. Evolution never got anywhere close to that. Why not? We're selecting for V. We're selecting for this thing to move quickly.
We're penalizing for hitting walls, so if you're going too fast, you have to kind of still slow down to turn and whatnot.
Possibly. If I remember correctly, these investigators also were able to manually drive the robot. And I think they had a grad student driving the robot who got really good at it and could drive the robot at close to 80 millimeters per second and still take the turns. So it's possible, but evolution didn't produce the solution. What happened here?
I don't know what evolutionary algorithm they used, but it could have reached one peak that wasn't actually the highest peak.
Like we talked about in lecture 5, right? It might have got trapped on local optima. I think they checked that too. Not the problem. This one's really subtle. For the engineers in the room, they might be able to figure this out.
It penalizes deceleration.
It penalizes deceleration. Yeah. So don't decelerate. Go fast and turn really quickly. It's possible the grad student figured out how to do it, could drive the robot.
To make a sharp turn, the difference in motor speeds needs to be high.
Okay. Yes, that wasn't it either.
When it's first starting up, its like acceleration speed difference is going to be really high.
Okay, so there's acceleration, deceleration arguments to be made as well. The sensors, remember this is 1993, 94, 92, early 90s. The sensors at that time had a certain refresh rate. So they would take their values, they'd send out their pulse of infrared light, and then measure how long it took for the light to come back. Send another pulse of infrared light, another pulse. There's a certain polling frequency of these sensors. So imagine I took you over to Patrick Gym and we made a big maze over there, and you had to run around, but I would turn off the lights for 3/4 of a second and then flick them back on for 1/10 of a second, 3/4. You're not going to run at your top speed. So the robot is intermittently blind, and it seems like the fastest it can do at doing this task, including all the other problems we just mentioned or the other constraints, it was being limited by the refresh rate of the sensors. If we went back and did this experiment today with 2026 sensors, I'll bet you this robot would evolve to drive much faster.
Could you have added a penalty to like minimize the difference between the max speed that it achieves and the actual top speed it can perform, so that as it goes it kind of tries to get faster and faster?
Well, that V is doing that, right? V is rewarding for faster and faster. I tell you in the maze over in Patrick Gym, you're not going fast enough, go faster. So you go faster and you crash into the walls because you're intermittently blind, right? This is, again, not the optimal. We don't know what the optimal is, but it's approaching as fast as it can control its motion, given the limitations of its sensors. Again, we are also limited by our sensorium. There's certain things we can only do because of limits in our sensors. It's always going to be true. Here's evolution implicitly getting close to the limits of what's possible, given the constraints of the hardware of the robot. Yeah? Question?
Well, I was also just gonna point out
Yep.
that, like, if we're just talking about an instantaneous speed, that it's possible to go around the maze faster if your maximum instantaneous speed is like slower than someone else, because I mean this is an extreme example, but like you can see the way it's evolving. It's not like if you're thinking of like driving a car, there are certain times where you would want to actually not take, well, most of the time you don't want to actually take a turn super tight because of things like traction, so it might make more sense to like go wider and cut in, but
True,
yeah.
true. Yeah, absolutely, right? There's real constraints here. Can't take the turn, possibly couldn't take the turn too fast. The grad student could take the turns at 80 millimeters per second. Again, this is great. We're pointing out a lot of constraints that are coming from the robot, from Newtonian mechanics. You can't turn at too much of speed. You might Tokyo drift and all those sorts of things. Not at this size scale, but again, these things matter, especially if you're building autonomous vehicles. Question?
Is it a little unfair to the robot because the grad student knows, he remembers where to go fast and where to go slow, but the robot doesn't?
Great point. Absolutely. The grad student had several advantages over the robot. First one being, as you mentioned, a God's eye view, right? The grad student, while driving the robot, can see it's approaching a curve. The robot may or may not be able to see it's approaching a curve, but probably not as well as the grad student, because the grad student is a human, and humans have very good visual sense, right? Our visual sensors update way faster than these proximity sensors do. Absolutely, the grad student had an advantage, which is why they could learn to drive the robot this fast. This is as good as evolution could get the robot to do under the constraints that the robot has to operate under. Yep.
If you were to add more sensors that are firing at different times, would that allow you to go much faster? Or
Fantastic, absolutely, right? So I don't know whether these 8 sensors were refreshing or pulsing in sync. If they were, that was probably not a good design decision. We could add more and put those pulsed infrared sensors out of sync. They'd be sending out signals at different times. And assuming this relatively simple neural network can deal with that wrinkle in the design, maybe this number would climb higher if we re-evolved it. Absolutely. You're talking about now making a physical change to the robot, which is what we're going to get to later in the course, right? Evolution does best when it's able to tinker with body and brain simultaneously.
They just use the same fitness equation the whole time.
Absolutely. Everything you see here came from this.
Did they ever try it with like a different fitness equation?
I'll bet you, I know the investigators, I keep meaning to ask them, I'll bet you they ran phi equals v times 1 minus I to start with, and it didn't work. They probably got this or something else. All of these little subtle details you see, they were probably added in retrospect because the original fitness function didn't work very well. They probably did some fitness function engineering. Okay, I want to move forward. If you thought that experiment was fun, this is the gantry robot created at the University of Sussex. So we just talked about the Italian approach. This is the English approach. This experiment was conducted and reported in the literature at about the same time. So everyone in the field has just decided to give them both the gold medal. These were simultaneously the first experiments in this field. Okay, so what is the gantry robot? Again, we've got a 90s desktop sitting over here, connected by a tether to the gantry robot. They cut a big hole in a table and put on top of the edge of that table an X trolley. So this is a wheeled vehicle that rolls back and forth horizontally along the table. That's the X trolley. And on top of the X trolley, they put a smaller Y trolley that drives vertically up and down the length of the X trolley while the X trolley is moving. They then hung an upside down camera underneath. So this camera is pointing straight down. Here's a close up. The camera's in here. And underneath that camera, it's better, you can see it better here, they put a little dental mirror, a little circular dental mirror. And they have a motor underneath the dental mirror that's spinning the dental mirror around and around and around at a continuous rate. You're going to see a lot of crazy robots in this class. This is one of the crazier ones. Who would ever make such a machine, and why? What's the point of this odd design?
It looks like it's gonna like scan like some kind of area.
It's going to scan, it says here, Toy Town. So they can put, obstacles and things underneath. So instead of driving a little robot on top of a table, the robot is going to drive, quote unquote, through Toy Town that's set up on the floor. That's a strong hint to why they set it up like this. There's a reason why it's set up like this. It's going to make life easier for someone. What was the most painful part of the Italian approach? There was the sheer amount of time, but
The manual like setup.
the manual setup. So here they had a little script, a few lines of code that after every set of synaptic weights is executed for 10 or 15 seconds on the gantry robot, that script would take over and it would send commands to the X trolley and the Y trolley that would basically reverse the path, and the gantry robot would reset itself. So this also ran for days and days and days and days, but there didn't have to be a poor grad student there's hitting enter or moving the machine. They could automatically reset the robot after the evaluation of each set of synaptic weights. So the gantry robot, among other things, is more automated than the Kepra experiment. Yeah? Okay, so what can the gantry robot do? First of all, we want to think about how it moves. There are 3 ways it can move, or 3 degrees of freedom. Remember our discussion about movement and degrees of freedom. So there's 3 motors in this experiment. Motor 1 drives the X trolley. Motor 2 drives the Y trolley, and motor 3 is always on, and it just rotates the dental mirror to give the downward pointing camera a 360-degree view horizontally around the robot. You'll notice that the dental mirror is angled at 45 degrees, right? So this 45-degree mirror is spinning. So it's basically an upside-down periscope. It is an upside-down periscope. Yeah? Okay. All right, so hold on to that. We got 3 motors. We need some sensors for our robot. Turns out that the gantry robot has 7 sensors. 7 sensors, 3 motors. What are the 7 sensors? Well, they put a little plastic disc underneath the motor that rotates the dental mirror. And they attach this little plastic disc to it. There's a little touch sensor underneath here that you can't see. So whenever this plastic disc gets bumped by a toy in Toy Town, it'll bend or deflect the underlying disc. They took the raw numbers arriving at the touch sensors and turned it into 4 binary values. Did the disc just get bumped from front right, back left, or front left? Again, they're using early 90s technology, so they're kind of simplifying the sensors, the values that can arrive. So for our purposes, I want you to think now about 4 sensors or 4 sensor neurons. And at every moment in time when the gantry robot is running, those 4 sensor values have a value of either 0 or 1. They're indicated whether or not the robot got bumped from that respective direction. So far, so good? Okay. All right. The 5th, 6th, and 7th sensor are report visual information. This is the most complicated and non-intuitive part of the gantry robot, of which there are many non-intuitive parts. Okay. Remember that we have this constantly spinning mirror and the camera. So from the point of view of the camera, it is getting a 360-degree view, which is a little confusing here. They've shown it with north, west, east, and south. I want you to think about this square as a panoramic view horizontally around the robot. Okay. They rotate the image. They do a little bit of image processing, which we're not going to talk about now. They then took from that, each frame of that video, they threw a lot of information away. If you remember the BabyBot experiment, we also saw a case where they threw a lot of visual information away. For the BabyBot, it could only see motion or non-motion. In the case of the gantry robot, they're going to throw away all color information. So they're going to turn the images coming from the camera into grayscale. And then they drop 3 circles. These circles can have different radii, as you see here. And these circles can exist at different positions within the 360-degree view of the robot. Might be hard to read. This says receptive field. You can think of this as the receptive field or the fovea of the robot. You have a fovea at the back of your eye. I think we mentioned this before. If you pay attention to what you're seeing, you'll notice that you actually only see a non-blurry image that's very, very small right at the center of your vision, and everything else is blurry. The fact that that little piece is non-blurry is because of the fovea sitting directly at the back of your eye. Most animals and most predators have fovea. They have very non-blurry, very good vision directly in front of where they're looking for obvious evolutionary reasons. They're doing the same sort of thing here, except they're giving the gantry robot 3 different fovea, and those fovea can be bigger or smaller. It's kind of an odd, arbitrary choice, but bear with me for a moment. For every image arriving from the camera, they take all of the pixels inside each of the 3 fovea and take the average brightness, the average whiteness of the pixels inside that fovea. So this fovea is picking up some dark object here in the 360-degree view. This fovea is picking up intermittent brightness somewhere else in its view, and bright colors or brightness somewhere else in its field of view. We have 3 fovea. We're taking the average brightness, which gives us 3 floating point numbers pulled out of the visual field, and then they finally discretize those 3 floating point values to 3 integers between 0 and 15. They did some fancy software here that ran faster with integers than it did with floating point values. They're dealing with, early 90s technology, and they're getting frames from the camera, I think about 1/10 of a second, possibly faster. So there's a fair bit of software engineering and optimization that went into this, which isn't important for our purposes. What is important is that they're borrowing one biologically inspired detail, something that comes from our physiology. They've got 4 numbers representing tactile information and just 3 numbers, 3 integers, representing something about the visual field. So the gantry robot, like the Kepra, is also almost blind, but in a different way. Everybody see that? No pun intended. Okay, so we've got, at every moment in time, the gantry robot gets 7 incoming sensor values, and there are 3 values, there are values arriving at the motor neurons that control the X trolley and the Y trolley. In the neural network that controls the gantry robot, there are only 3 motor neurons, but there are 3 motors. X trolley, Y trolley, and the spinning mirror. They don't control the motor that spins the mirror. They're just using that motor to help give the 360-degree view around the robot. So the gantry robot really, the neural network driving the gantry robot is only going to control the motion of the X trolley and the Y trolley. Okay, very odd robot. Any questions about any of that?
So the 3 visual inputs, are those just supposed to be objects it's detecting out in the world?
We haven't said yet. Are they supposed to be objects? We haven't actually said anything. I mentioned Toy Town. They did lots of different experiments. We'll see in a moment about what they exposed the robot to under the table in a moment. Yes?
In comparison to the Italian approach, like the robot itself and the control scheme is completely different. Is it supposed to be comparable and like the competitor to that style of robot, or is it supposed to have a different task? Because like one, it's handling rotation, like movement. The other, it's just moving, like handling translation.
Yes, they were not competitors. Evolutionary robotics is a small field. Everyone knows everybody else. They weren't competing. I think they're mostly working independently, right? There's kind of independently discovering that you could use genetic algorithms or evolutionary algorithms, which had been around since the 70s, and you could apply it to 90s robotics technology. You could cobble together a robot, and this idea of evolving brains for robot I think it was kind of emerging in these 2 places at the same time. So not surprisingly, they came up with very different solutions. They're kind of playing with this new idea, and there's 2 very different ways you can play with it. Okay, all right, so now let's talk about what they evolved the gantry robot to do. So we've got phi here, so we're going to go back to creating some fitness functions. In the experiment we're talking about today, they did not use Toy Town. What they did is they dropped colored cardboard below the back of the table. So apologies for my 3D graphics here. This rectangle is closer to you. This is underneath the front of the table. And this rectangle here, this is underneath the back of the table. And they're dropping a piece of gray cardboard. Remember, the gantry robot can see horizontally around itself. So in theory, it can see that there's some gray back here. They're going to eventually start to put shapes, different shapes back here. And ultimately, the task they want to evolve is discrimination. As you'll see in a moment, they're going to evolve the robot, the gantry robot, to be scared of rectangles and to love triangles. It's like a version of a Bratenberg vehicle. Yeah? Go away from your foes and go towards your friends, right? That kind of thing. You need to be able to discriminate in this world to survive. They're going to run this evolutionary algorithm incrementally. We're going to see this several times throughout this course. So incremental evolution is an evolutionary algorithm where you evolve against one fitness function for a little while, and then when the robot gets really good at doing that thing, You swap out that fitness function and put in a more difficult fitness function, and then a more difficult fitness function, and so on. This idea of incremental evolution, evolving something to do something simple, like just approach the back wall, and then evolve it to do harder and harder things, is an idea that's now stolen from developmental psychology. The concept of scaffolding. We already talked about how much time humans spend on our little children for obvious reasons. A strategy parents and caregivers use all the time is scaffolding. We don't teach calculus to a 4-year-old. It's probably not going to work. We teach them other things first. We give them easier tasks and gradually make the task harder and harder. That's scaffolding. This is a version of scaffolding here. Best example of scaffolding is training wheels on a bicycle. Allow the little human to get a sense of what it means to actually ride a bicycle. Once they start to signal competence, in our case, the fitness value rises above some threshold, take off the training wheels. Okay, here we go. They're going to evolve sets of synaptic weights, just like we saw before, to drive the neural network of this robot, to approach the back wall from 4 different initial conditions. So for every set of synaptic weights, they're going to drop that set of synaptic weights into the gantry robot 4 times. And each time, at the beginning of each of those 4 times, that script I told you about is going to drive the X and Y trolley to some random position underneath the table. We were discussing a few minutes before about generalization. These experimenters are trying to evolve a robot that can see and move towards the gray rectangle regardless of where it starts from, under the table. Okay. We'll come back to the fitness function in a moment. We're going to assume that it evolves to do that. No matter where we put the gantry robot under the table, it always sees and moves towards the back gray rectangle. So now they're going to keep the set of synaptic weights. The only thing they're going to throw away is the fitness function, phi1, and they're going to swap in a new fitness function, phi2, which is going to evolve sets of synaptic weights to approach the gray rectangle that's placed at different horizontal positions underneath the back of the table. So the robot has to show us that it actually knows where the rectangle is. In this earlier case, the sets of synaptic weights might evolve such that the robot ignores the grayness and just always drives backwards. In other words, it might evolve to always drive the Y trolley to the top of the X trolley. Doesn't necessarily even need, in this first stage, to learn how to evolve to recognize the gray rectangle. But here, if we put the gray rectangle back right at the back right of the table, we want it to the gantry robot to always drive to the back right under the table. Everybody see that? Okay. Seems kind of trivial. Once it evolves to do that, now they're going to put a triangle and a rectangle underneath the back of the table, but they might put the triangle on the left and the right, the triangle on the left, rectangle on the right, or the rectangle on the left and the triangle on the right. And the robot should go away from the back rectangle and approach the triangle. Okay, let's have a look at the fitness functions. First one evolves to maximize distance from the back wall. Maximizing the distance from the back wall would actually result in the opposite of what we want, right? That would be driving to the front of the table. This is an annoying thing about evolutionary robotics experiments. In one experiment, they're trying to maximize the fitness function. In other experiments, they're trying to minimize the fitness function. So here they're trying to minimize distance from the back wall. Lower phi is better. The second experiment, they're using DI, which is minimize the distance of the robot from the center of the rectangle. You'll notice that these fitness functions are a summation from 1 to 4. So we're summing up how well the robot does in each of the 4 cases. So far, so good? Okay, last one. I'm going to go through this quickly because I want to finish up this lecture today. In this case, they're trying to minimize this stuff here, which is minimize the distance to the triangle and maximize the robot's final distance from the rectangle. I'll leave it to you to work out from that verbal description back to the math. So basically, phi 3 says be as far away from the rectangle as possible and be as close to the triangle as possible at the end of the 10 or 15 seconds of evaluation. Okay, so we've run an evolutionary algorithm now. Phi 1 starts to climb over evolutionary time. Phi 1 gets above some threshold. We swap in phi 2. And the value of phi 2 for all of the individuals in the population is probably low because they were never evolved against phi 2. Phi 2 starts to climb over evolutionary time until it gets above some threshold. They swap out phi 2, swap in phi 3. Phi 3 is probably a little bit low, starts to climb. And at the end, they have one set of synaptic weights that reliably drives the robot, the gantry robot, towards the triangle, which is at the back right of the table, and stays away from the rectangle. Seems like kind of a trivial task, but again, this was a big success at the time. Here's the initial position 1, initial position 2, initial position 3, and initial position 4. Is this optimal? Yes?
Out of curiosity, with the 4 or the 3 phobia, is that randomized each time, or
yeah.
does it stay constant for each robot?
Thank you. I forgot to mention that. I forgot to mention that detail. They're evolving sets of synaptic weights, so they're evolving parameters describing the brain of the robot. They are also evolving, with the set of synaptic weights, they tack on an additional 9 numbers, which describe where to place the fovea. So over evolutionary time, the positions and radii of these fovea is also changing. So what are those 9 additional numbers that are in this vector? This vector contains values for the synaptic weights and an additional 9 floating point numbers. There's 3 triplets. They break those 9 numbers into 3 triplets. Each triplet describes where to place each of the 3 fovea, what x, y position in the camera frame, and the third number in the triplet is the radius of that fovea. So it could evolve to put all 3 fovea right in the center of its visual field. It could be put one up here, one down here. Basically, in this experiment, they're going to evolve the brain and the ocular physiology, physical details of the eye of the robot over evolutionary time. Thank you for pointing out. That's a very important detail that we'll get to in a moment. Is the robot moving optimally? Is the robot with the most fit set of synaptic weights and the most fit placement of the 3 fovea? Is it achieving this task optimally?
Occasionally, but often it gets stuck looping around.
It's looping around, right? Doesn't seem optimal, right? Intuitively, we want it to make a beeline for the triangle and kind of bend away or stay away from the rectangle at the back left, the evil rectangle at the back left of the table. Why is it doing this corkscrew motion? Kind of a trick question. There's no way we can know at this point. Seems like kind of an odd thing to do. Again, I'm sorry about the quality of this image. I will walk you through it. This is the evolved brain and the evolved ocular physiology, how they structured the eye of the robot. Let's hope, there we go. Okay. So let's talk this through. On the left-hand side here, this is, these are the 2 sensor neurons that actually affect the 2 motors. There's the left motor and there's the right motor. Sorry, there's the left motor and there's the right motor here. Left motor, right motor. All these other neurons, this one, this one, this one, this one, this one, this one, these are all hidden neurons. So we have perception arriving here and actions being sent to the left and right motor here. I think this is a typo from the paper. It should be X trolley and Y trolley. There's no left and right motor here. Okay. You'll notice that in the little picture here, there isn't the third fovea. So it turns out that the third fovea is actually there's a sensor neuron here associated with the third fovea. That third sensor neuron is receiving the brightness falling in that third fovea, but there are no connections, there are no synapses that wire up that third fovea to the two motor neurons. So a lot of the synaptic weights have been set by evolution to 0 or 0.000001 to basically be ineffectual. So this is evolution showing off. Remember that there are 7 sensor neurons. There's 4 pieces of touch information which are never used. They're kind of thrown away by evolution. Why? Why is it not using touch information to drive the trolleys?
Because if it can just see its environment well enough, it doesn't need to touch anything.
There's no obstacles in the environment. There's nothing to hit. It doesn't need touch information.
Oh.
It also doesn't seem to need this third fovea. We got 4 minutes left, so we're going to try and crack the mystery of these 2 fovea. It's placing one fovea here and the second fovea diagonal from it. So I'm going to have to add some details here. I mentioned that it scans horizontally around it. I want you to, basically where these 2 fovea are being placed are actually vertical in the frame. Meaning, from the point of view of the gantry robot, it's looking around like this. It's got a 360-degree view, but it's also turning, and these 2 fovea, as it's turning, can move horizontally. Or as it's driving, as it's moving, these 2 diagonally placed fovea are touching different parts of the visual scene of the robot as it's moving. Okay? If it moves to the left, for example, relative to the back wall, fovea 1, the one in the upper left, will hit the right-hand edge of maybe the rectangle. And then if the robot keeps moving to the left, the second fovea is going to hit this edge of the rectangle. So imagine, again, you're looking through your fovea and you scan your head and someone in this room comes into focus at a certain point in time and then another person comes into focus. That's kind of what's happening here from the perspective of the robot. If the robot moves left and sweeps its fovea across the rectangle, fovea 1 goes dark and then fovea 2 goes dark. So far, so good? Here's fovea 1, here's fovea 2. So that information is going into the neural network and affecting how the robot moves. Alternatively, if the robot moves left and fovea 1 hits the right edge of the triangle, fovea 1 goes dark, and then fovea 2 also goes dark. This robot is demonstrating that it knows the difference between the rectangle and the triangle. How? How does it know the difference? We're not feeding in raw pixel information. It doesn't see a triangle and run a triangle detector module. What's happening here?
Is the triangle always upside down?
It's always upside down. Yeah, you can think about it as the tip here is touching the ground.
It's just like when the 2 foveas see it and like when it goes dark because it's at an angle rather than straight down with a rectangle.
When? What is the time interval between fovea 1 going dark and then fovea 2 going dark. In the verbal description I just gave you, that time interval is going to be shorter for the rectangle than it is for the upright triangle. It's going to go dark, and then a longer period later, fovea 2 is going to go dark. There are some recurrent connections in this neural network. Remember that recurrent connections signal memory. This neural network is holding on to some information from the past. Somewhere in here, it's holding on to information about when fovea 1 went dark and when fovea 2 goes dark. We're out of time, so I just want to try and wrap this up. Of everything you're going to see in the course, this is my favorite example of embodied cognition. This is a very, very simple neural network. It's bringing together, it's integrating information about movement, shape, time, brightness, visual information. It's combining it in a very non-intuitive way, not how we would probably design a robot to distinguish between triangles and rectangles, but it works very, very well. It's a simple but good solution. Because it's simple, it actually probably generalizes better than more complicated approaches. And it's integrating information about the world, physical information about the world, information about itself to solve this task. Okay. We'll talk about CTRNNs next Tuesday. You're working on assignments 4, 7, and/or 8. See you next week. Thank you.